Okay, let me start. What I want to talk today is about algorithms and how we interpret them, machine learning algorithms in particular, and I'm going to tell two stories. And these stories together, I think, will give us some guidance, hopefully, about this problem. The first story is not really work I've done. The first story is work that a Google team did a few years ago. So this was early days before there was a lot of work on machine learning algorithms applied to medicine. So there they said, we have a huge data set with x-rays, and in the x-rays we have labels on whether there's a problem. So they said, let's build a pathology detector. And so that was their goal of the project. And what they found, this is pretty early, they found remarkable success in this activity. And it was almost too good to be true. But they were like, well, this is really interesting, so let's go and have a look and see what the algorithm is seeing in the x-ray. So they applied attribution techniques of the kind that you're all probably familiar with, where we can see which pixels were most influential. So in doing this, they saw, okay, well, look, on this x-ray, this is where the algorithm is really noticing signal or picking up on signal. So why here? So let's kind of zoom in and adjust the contrast and say, wait, that's a little weird. That doesn't look like it's part of the lung. What is that? Well, it turns out to be pen marks by the doctor. So what they thought was a pathology detector was actually a pen mark detector. Radiologists in the system from which the data came, when they looked at the x-ray and they saw something, they'd put a little pen mark on it. And so as a result, the algorithm learned to find pen marks. But of course, this is a disaster. You can't deploy an algorithm that was a pen mark detector to say, now we have a pathology detector. This is the kind of problem we all worry about when training machine learning algorithms, that instead of picking up the signal we want, it's picked up some other thing that's an artifact of the data set, that's a confounder. This is why we have interpretability techniques at some basic level. In fact, I want to say this story is just a nice encapsulation for me of how we tend to normally and most often use interpretability, which is quite similar to how in another aspect of computer science what we tend to do, which is when we program, we tend to debug code. Similarly, here interpretability is being used to debug the machine learning pipeline, like problems in the data, things that aren't what we want. And since these algorithms are black boxes, we can't know what they're doing, so we use interpretability to try and get a handle on that to make sure they're doing what we want them to do, much like with traditional code. Okay, that's story one. Story two also involves x-rays, but this time it's about osteoarthritis. Osteoarthritis, for those of you who don't know, is a very painful degenerative condition, and in this case we're going to focus on the knee. It happens in many joints, but knee osteoarthritis is sort of the space between the bones, there's sort of lost cartilage and the meniscus is worn down, and so it's painful whenever you walk or move. So it's not a pleasant condition. And many people have this chronic condition. And the big consequence here is pain. Now, the story I want to tell about the pain is that it turns out that, well, here's how we measure it. We ask people suffering from osteoarthritis, tell us on the scale how much pain you have, and there's an official pain scale, KOOS pain score. What researchers have found when looking at the pain experienced by those having osteoarthritis is that actually we find that the disadvantage in the United States, African Americans, low income, a lower education, experience much more pain, which is kind of tragic. They're sort of not just disadvantaged socioeconomically, but also physiologically, they're experiencing more pain by quite a bit. It's about 2/3 of a standard deviation by race. So why is this? Well, there are two theories, broadly speaking. Of course, there are many theories, as with all things. One theory says it's inside their knees. That's because of their lives, the disadvantaged have more physical ailments. So when they have, everyone had, who in the sample had osteoarthritis, but those who were disadvantaged had a more severe case of it. The other is that it's outside their knees, which is sort of non-knee-related factors that might be driving this, life stress, etc. And this is also very tragic. It's that the conditions of poverty or disadvantage exaggerate physical pain. Of course, a very related view is it's not inside their knees. It's just, the survey measure is biased. But to me, there's two categories. Is there something in their knees versus is it something else is pretty big. So how do we get at this? Well, the way we would get at this is that we would we of course have one read of the problem, the pain score. Well, now we get the x-rays, let's get a clinician to look at the read, get a KL grade. That's the grade of osteoarthritis severity. And now ask, conditional on the KL grade, the severity of the osteoarthritis in the knee, is there still a pain gap? And what we tend to find is that in fact, even after you control for the severity, that's on the x-axis here, you see that the gap barely changes. So by this data, people have said, wow, it's not a physiological problem, but something else, a psychological, sort of socioeconomic, or perhaps a measurement artifact. But is this really true? What did we actually do? We had a person look at the x-ray. I don't know, maybe there's stuff in the knee that the clinician didn't know to look for. I mean, medical knowledge is a limited thing that's still in flux. It's why we're still doing science. So let's instead have an algorithm look at the x-ray and predict pain directly. Now you'll notice, if there was something in the knee, the algorithm, given only the knee x-ray, ought to find it. If there's nothing in the knee, and it is psychological, given just the x-ray, it ought not to find it. So rather than conditioning on the KL grade, let's condition on this algorithmically generated thing. In fact, rather than relying on what doctors know to look for, let's ask an algorithm to look and see, is there some physiological correlate that you see in the knee about this? So ironically, what we're using here is we're actually saying, let's use a machine learning algorithm to listen to what the patients are telling us, my knee hurts, and try to isolate if there's something in the x-ray. So the input is image of both knees, and the output that the algorithm is trained on, the label, is the KOOS pain score in the knee. It's important here, only the knee is given. That is, we'll come back later, but it's not like the algorithm is able to reconstruct. We certainly aren't giving it any of the other variables, and such as race, education. We're only giving it the x-ray. And we'll deal with the possibility that the algorithm has somehow reconstructed these other variables. Okay, but the key is it only sees x-rays, doesn't have access to anything else. What we find here is that when we condition not on the doctor's score, but on the algorithmic prediction, that's on the right-hand side, the gap significantly diminishes. So while doctors don't see anything in the knee, algorithms definitely do. It's in their knees, which is what people have been telling us all along. And you can look at our paper, but we deal with all the obvious things. Is it image artifacts? Is the algorithm just predicting race somehow? A bunch of these things. What I want to do is to connect these two different stories back together. Both were about x-rays. Both are going to involve interpretability, because now you're going to ask me, wait, what is the algorithm seeing? But what the algorithm is seeing in this second story is a different thing than in the first story. Let me tell you why. There are two different approaches. In the first story, we were having the algorithm predict the physician judgment. In the second story, we're having the algorithm predict the pain score. And in that difference, in that choice of label, is the entire story. When we predict KL grade, we're trying to automate human behavior. When we predict pain score, we're looking for things that we don't know about. When we're automating, interpretability is about debugging. We know what we want, just do it. When we're doing prediction, as this story just ended, we're like, wait, you found something I didn't know? Well, what did you find? Interpretability for discovery is a fundamentally different problem. So when we took the known interpretability techniques to apply it to this, it didn't produce much. Why? Because we don't exactly know what we're looking for. It's not a bug that we're looking for. As a result, interpretability for discovery is what I hope to encourage all of you is an interesting area to work on. It's much closer to visualization. It's kind of look at the data to learn. It involves feedback loops. I don't know, what is the algorithm saying? You're okay with low recall. Anything in the knee the algorithm saw, any new signal is useful. And this activity of interpretability, I think, has not had the kind of tools associated with it. Most of the tools that we tend to have are implicitly, though not explicitly, focused on finding flaws in the algorithms we have. So I hope to leave with these two stories as a call to action that this is a really interesting kind of interpretability to work on.